Determine all intervals of concave up or concave down and determine the coordinates of all inflection points, including cliffs, for the function f of x equals x times 4x minus 40 to the 2/3. The first thing to do is find the domain. F of x equals x, a polynomial term, the domain will be all real numbers, times 4x minus 40, another polynomial, to the 2/3, a fractional exponent. The denominator of a fractional exponent is the root. It's an odd number here, and the domain of an odd root is all real numbers. Therefore, collectively, the domain will be all real numbers, or negative infinity to positive infinity. The next thing to do is find all candidate numbers. We will need the second derivative for this. We will start with the first derivative. F of x is a product of two expressions of x. The first derivative will require the product rule. F prime of x equals, the derivative of the first is a 1, times the second left alone, plus the first left alone, times the derivative of the second, which is a power rule. Bring the power down. Leave the inside alone. Subtract 1 from the power. I will call this 3/3. And then multiply by the derivative of the inside, which is a 4. The first term is 1 times an expression. 1 times anything is that same thing. So it'll just be 4x minus 40 to the 2/3. The second term, we can collect the constants together. There's a 2/3 and a 4. Multiplying the numerators, 2 times 4 is 8 over the 3. There is an x, and there is the 4x minus 40 to the 2 minus 3 negative 1/3 power. We can take the second derivative directly from here because the first term is just the power rule, and the second term is just the product rule. So, f double prime of x equals, the derivative of the first term is power rule. Bring the power down. Leave the inside alone. Subtract 1 from the power. I'll call this 3/3, times the derivative of the inside to complete the chain rule, plus the second is a product rule. We'll have the derivative of the first, which will be 8/3, times the second left alone, plus the first left alone, which will be 8/3 x, times the derivative of the second, which is a power rule. Bring the power down. Leave the inside alone. Subtract 1 from the power. I will call that 3/3. And then multiply by the derivative of the inside to complete the chain rule. For the first term, we can bring the constants together. 2/3 times 4. Multiplying the numerators, 2 times 4 is 8. It'll be an 8/3. And then a 4x minus 40 to the 2 minus 3 negative 1/3 power. We'll leave the second term alone, as is. It'll be 8/3 4x minus 40 to the negative 1/3. And for the third term, we can bring all the constants together. There is an 8/3, a negative 1/3, and a 4. Multiplying all the numerators, 8 times negative 1 is negative 8, times the 4 will be negative 32. and the denominator is 3 times 3 is 9. So negative 32 over 9. There is an x, and there is a 4x minus 40 to the minus 1 minus 3, which is minus 4/3 power. The first and second terms can be combined with each other since the power of the 4x minus 40 is the same. We can just add the coefficients, 8/3 plus 8/3. They're already over a common denominator. 8 plus 8 is 16/3. So we have a 16/3, 4x minus 40 to the negative 1/3 power, and minus 32/9 x times 4x minus 40 to the negative 4/3 power. We want the second derivative as a single fraction with all powers positive and fully factored. We have negative powers here. One option is to move them to the denominators of each of their terms, find a common denominator to make it a single fraction, and then fully factor the result. Another option is to factor it as is, which is usually quicker and easier. For the coefficients, the numerators, we have a 16 and a 32. We can factor a 16 out. For the denominators, we have a 3 and a 9. We actually want to factor out the lowest value, which is a bigger denominator. So we actually want to factor out the bigger denominator, which is a 9. There is also powers of 4x minus 40. We want to factor out the lower power, and that'll be the negative 4/3. It's lower by being more negative. So 4x minus 40 to the negative 4/3. Factoring out the 16 numerator, this will become a 1. This will become a 2. Factoring out the 9 denominator, the first term, factoring a 9 out, we have to first put it over 9. Right now, it's 1 over 3. But instead of writing it as 1 over 3, we can make it a 9 by turning the 1 into a 3. It's a 3 over 9. And factoring the 9 out leaves it as a 3. And then for the second term, factoring the 9 out, it will become a 1. So we actually have a 3 for the first term and a minus 2 for the second term for coefficients. Factoring out the 4x minus 40 to the negative 4/3, factoring is division. Division is subtraction of exponents. We will be subtracting a negative 4/3, which is equivalent to adding a 4/3. For the first power, negative 1/3 plus 4/3 is 3/3, or the power of 1. So we will have a 4x minus 40, and then times the 3 that sits in front of it. For the second term, we'll be adding a 4/3. Negative 4/3 plus 4/3 is the power of 0. Anything raised to the power of 0 is a 1. And so that will just be a minus 2x. So we have a 3 times 4x minus 40 minus 2x. A 3 times 40x minus 40. And then minus a 2x. So we have 16/9 4x minus 40 to the negative 4/3. Inside the square brackets, we can distribute the 3 in here. That'll be 12x minus 120. And then minus 2x. So f double prime of x equals, we have a 16/9, we have a 4x minus 40 to the negative 4/3, and inside the square brackets we can combine like terms together. I will change this into parentheses now. 12x minus 2x will be 10x, and then minus 120. There's a common factor of 10 there that can factor out. It will move all the way to the front to multiply with the 16/9. Multiplying the numerators, 16 times 10 will be 160. So we'll have 160/9. There will be a 4x minus 40 to the negative 4/3 power, and factoring out a 10 will be behind x minus 12. We want all powers to be positive so that negative power expression can now move to the denominator with the 9. The numerator will be 160 and x minus 12. And the denominator will be 9 times 4x minus 40 to the positive 4/3 power. So we have the second derivative written as a single fraction. All powers are positive, and it is fully factored at least for the portion that is not inside of a fractional exponent. No need to factor that. It has a common factor of 4 in there, but the fractional exponent is 4/3 power, which means cube root, and the cube root of 4 is not an integer, so it's best to leave that not factored. We can now set the numerator equal to 0 and the denominator equal to 0 and solve for all x's, starting with the numerator, 160 times x minus 12 equals 0. We can divide both sides by 160, x minus 12 equals 0, and add 12 to both sides, x equals 12. Now, the denominator, 9 times 4x minus 40 to the 4/3 equals 0. We can divide both sides by a 9, so 4x minus 40 to the 4/3 equals 0. And now we can raise both sides to the reciprocal of 4/3, which is 3/4. The reason we're raising it to the reciprocal is when we raise and raise again, we multiply the powers. Multiplying the numerators, 4 times 3 is 12. Multiplying the denominators, 3 times 4 is also 12. 12 over 12 is 1. And this will be 4x minus 40 to the first power equals 0 raised to any non-zero positive number is 0. We can now add 40 to both sides, so 4x equals 40, and divide both sides by 4, so x equals 10. We will now check to see which of these are in the domain. The domain is all real numbers. X equals 12 is a real number, x equals 10 is a real number. We keep both of them. They are both candidate numbers. We can now draw a domain line, a line representing the domain. It has no left end because it starts at negative infinity. It has no right end because it ends at positive infinity. We can put all candidate numbers on here in order. We have a 10, we have a 12. 12. This splits the domain interval up into 3 separate intervals. We can pick a test value in each of the intervals. The first interval is negative infinity up to 10. We can pick 0 in there. The next interval is 10 to 12. We can pick 11 in there. And then 12 to positive infinity, we can pick 20 in there. We can test the concavity in each of these intervals by plugging the test value back into the second derivative. We don't care about the value of the second derivative, we just care whether it is positive or negative. Therefore, the best place to plug in is the fully factored version, this one here. A couple of things about this. In the denominator, the 4x minus 40 is raised to the 4/3 power. That means cubed root, which could be positive or negative because it's an odd root. But then to the 4th power, since it's an even power, that will always make it positive. So that expression will be positive times the positive 9 will also be positive. So the entire denominator is positive and therefore it doesn't affect the sign of the second derivative. In the numerator, the 160 is always positive and therefore it also does not affect the sign of the second derivative. Therefore, the only portion that matters to determine whether it is positive or negative is the x minus 12. Plugging in the first test value into x minus 12, 0 minus 12 is negative. We have a negative second derivative. This corresponds to concave down. Plugging 11 into the portion of the second derivative that matters, 11 minus 12 is negative. We have a negative second derivative. This corresponds to concave down. And plugging the 20 test value into the portion of the second derivative that matters, 20 minus 12 is positive. We have a positive second derivative. This corresponds to concave up. So we have concave down happening from negative infinity up to 10, and union, because it is happening again, from 10 to 12. We cannot join those intervals together because they do not include 10. 10 was a candidate number and is not included on there, round brackets. So those are 2 separate intervals. We have concave up happening from 12 to positive infinity. Right at the candidate number of x equals 10, we have the concavity not changing. It's concave down on the left and concave down on the right. So x equals 10 is not an inflection point because the concavity did not change. What it would be is concave down on both sides. It actually is a cusp minimum. But that's something that would be determined by the first derivative. Right at the candidate number of x equals 12, we do have the concavity changing from concave down to concave up. So x equals 12 will be an inflection point. So we have an inflection point with an x-coordinate of 12. It will have some corresponding y-coordinate, which can be found by plugging the x-coordinate back into the original function. So y will equal f of 12, which is going to be 12 times 4 times 12 minus 40 to the 2/3 power, which is 12 times 4 times 12 is 48 minus 40 to the 2/3 power, which is 12 times 48 minus 40 is 8 to the 2/3 power. So this will be 12 times 2/3 power. The denominator of the fractional exponent is the root, so it's cubed root. Cubed root of 8 is a 2. And the numerator of the fractional exponent is the power, so it'll be 2 and then squared. 2 squared is a 4. 12 times 4 is a 48, and there's the corresponding y-coordinate for the inflection point. So we have 2 intervals of concave down. We have 1 interval of concave up. And we have an inflection point occurring at 12, 48.